Using the kinetic theory, we found that the root mean square speed of ideal gas molecules is the square root of 3 kT over m. We also know that in an ideal gas, the molecules interact only when they collide in perfectly elastic collisions. They do Brownian motion. As shown in this video, there are 800 particles in this simulation. The 5 yellow particles leave 5 blue trails of random motion, and one of them has a red velocity vector. You can see that the red velocity vector changes magnitude and direction after each collision. In 1860, using kinetic theory for ideal gas, James Clerk Maxwell predicted that at a certain temperature, the elastic collisions of molecules produce a very specific distribution of speeds called Maxwell speed distribution. The distribution is shaped like this. Here, the y-axis represents the number of molecules, or the probability of having speed v, and the x-axis represents the speed v. As we can see, there is a peak in this distribution. We call its corresponding speed the most probable speed. The probability of finding molecules with this speed is the highest. Since this distribution is not symmetrical and is skewed to the right, the root mean square speed is slightly higher than the most probable speed. The distribution varies with temperature. At a higher temperature, the distribution shifts to the right with more molecules at higher speeds. At a lower temperature, the distribution shifts to the left with more molecules at lower speeds. Here's an example of Maxwell speed distribution at 298 Kelvin for 4 noble gases: helium, neon, argon, and xenon. Which curve corresponds to which gas and why? According to the kinetic theory, the average kinetic energy equals to 1/2 m times the root mean square speed squared, which also equals to 3/2 kT. They all have the same temperature. And the 1/2, 3/2, and the k are all constants. Therefore, the bigger the molecular mass, the smaller the root mean square speed. This means a curve with higher probability at lower speeds would correspond to heavier molecules. So A must be for xenon, B for argon, C for neon, and D for helium.